Hello, my name is Pablo Ocal. I'm from Texas A&M University. And first of all, I'd like to thank the organizers of the Encuentro Virtual de Álgebra Homológica for the opportunity of giving a short communication. And I'll be talking about homotopy liftings and Hochschild cohomology of some twisted tensor products. And this is a joint work with Tolulope and Sarah Witherspoon. And it is based on work already posted on the archive. So what I would like to start is to motivate a bit what's the topic, and then I'd like to introduce you Hochschild cohomology because I'm aware that not everybody may be familiar with it, and I would also like to introduce some of the structures which we heavily use. Third, I'd like to introduce what twisted tensor products are, which are some non-commutative generalizations of the usual tensor product. And finally, I'll finish with some applications of our work and what I will be discussing and some future work that is possible along these lines. So let's start with the motivation for our work. So back in 2014, Li and Zhou proved that the Hochschild cohomology of the usual tensor product of two algebras is isomorphic to the tensor product of the Hochschild cohomologies of these algebras. So this tensor product is over the base field over which the algebras are a k-vector space, and the double H's are the usual Hochschild cohomology. Without getting too much into details, we'll review this in a bit. Now, as I mentioned, there is a non-commutative analog of the tensor product, which we call the twisted tensor product. And what it would be really nice is to have a similar behavior over it. So just like a symbol by symbol translation yields that the Hochschild cohomology of the twisted tensor product is isomorphic to the twisted tensor product of the Hochschild cohomologies. Unfortunately, the symbol by symbol translation cannot possibly be true. So the left-hand side is a graded commutative algebra, but the right-hand side, as we were mentioning, is in general a non-commutative algebra. So unfortunately, this is going to be true. So what we would like to, the question motivates looking at this is, okay, so if this cannot be true, what is the correct interpretation of Li and Zhou's result? So keeping this in mind, let's jump into a tiny bit of the technicalities, and let's look at the definition of the Hochschild cohomology. So given an algebra over a field, just to simplify a bit the story, we consider AE the enveloping algebra, which is the tensor product of the algebra with its opposite. And then we defined the Hochschild cohomology as the X group. So the nth Hochschild cohomology of A is the nth X group of A with coefficients in A, everything seen as algebra, as modules over the enveloping algebra, which is the same thing as bimodules over the original algebra. And then we can take the direct sum of all of these X groups, and we get that the full Hochschild cohomology is the direct sum of all the X groups of the Hochschild cohomologies of A. So this definition comes with a couple of operations. So we have the cup product, this is smiley, which is completely analogous to the cup product in topology and simplicial homology, for example. And it also comes with a Gerstenhaber bracket, this bracket operation. The cup product takes an element of degree m and an element of degree n, and gives an element of degree m plus n, while the Gerstenhaber bracket intakes an element of degree m, an element of degree n, and gives an element of degree m plus n minus 1. So it turns out, as we were mentioning, that the Hochschild cohomology together with these operations has a lot of structure, really a lot of structure. So with the cup product, it turns out that what we get is a graded commutative algebra with the Gerstenhaber bracket. The Hochschild cohomology has a structure of a graded Lie algebra. And if we put both the cup product and the Gerstenhaber bracket and we add some compatibility conditions, then it turns out that what we get is the so-called Gerstenhaber algebra, which is also known as a Poisson 2 algebra or a Poisson algebra with Poisson bracket of degree minus 1. Again, without getting into too many details and just to fix ideas, this last structure can be thought of as a graded Lie algebra coming from an associative algebra. And there are some key differences because if you want to be precise, as we've seen before, the degree of the Hochschild cohomology with respect to the Gerstenhaber bracket is 1 less than the degree of the Hochschild cohomology with respect to the cup product. So we have to be a tiny bit careful about the compatibility conditions. So keeping this in mind, let's look again at Li and Zhou's result. And we can now state the complete result, which is given two algebras over a field where at least one of them is finite dimensional. Then the Hochschild cohomology of their tensor product over the base field is isomorphic to the tensor product of the Hochschild cohomologies, again, over the base field. But this isomorphism is as Gerstenhaber algebras, like we cover the whole structure. And the proof of this, it works over a specific resolution and uses something called Alexander-Whitney and Eilenberg supermaps. But the part that I want to stress is that it's extremely cumbersome. So given this result, something that you may complain, I rightfully so, is that I have not told you how you can get a cup product or a Gerstenhaber bracket on this right-hand side. But for the time being, let's say that they exist and that they satisfy what they should satisfy, and that's a side comment. But indeed it should be defined, and Li and Zhou do so. So now that we have the result that motivates our work, let's look at some non-commutative tensor products. The case that we are interested in is the twisted tensor product, and these constructions come from a twisting map. So a twisting map is a map from the tensor product of B with A over the base field to a tensor B, and it's a bijective k-linear map satisfying a few conditions. One of them is that when we twist past the unit, it does nothing. So we can just twist the unit of B past any element in A and twist the unit of A past any element in B, and we recover what we originally had. And then we want to impose some compatibility conditions for the multiplication of the algebras A and B together with the twisting map tau. And this is what the commutativity of this diagram is doing. So we are asking that first twisting and then multiplying, that's going clockwise, is the same thing as first multiplying and then twisting, which is going counterclockwise. So once that we have such a nice twisting map, we can define the twisted tensor algebra, which we denote with this tau subscript on the tensor product. And this is the vector space A tensor B, and we define this new multiplication, which is first twisting and then multiplying. So we twist the pair B tensor A past each other, and then we multiply in A and we multiply in B. And it turns out that this operation is an associative multiplication. So now as we mentioned, we're interested in working with the Hochschild cohomology of a twisted tensor product B. But working with this is, of course, not to treat this twisted tensor product as just any given algebra, but to use some information about the original algebras A and B that we already know. And for example, if we have additional information about the resolutions of A and B to compute the X groups, or about the cocycles, or we know the Gerstenhaber bracket in the respective Hochschild cohomologies of A and B, then a combination of the results that follow allow us to compute the Gerstenhaber bracket in the full Hochschild cohomology of this twisted tensor product, which is a notoriously difficult task. So we'll see how some of this works. And for this, let's not consider the most general case of any twisting map. Let's consider, for the time being, just twisting by a bicharacter. So what I mean by twisting by bicharacter is that we have a couple algebras over a field, let's call them A and B, and they are graded by commutative groups F and G. And we have a map that's a bicharacter from the tensor product over the integers of F and G to the units of our base field. So given this bicharacter, then the twist, which is permuting A and B and adding a scalar multiple that corresponds to the degrees of A and B according to the bicharacter, then this twisting map induces the algebra structure that we call twisting by a bicharacter. So when we just write everything out, it turns out that twisting by a bicharacter, this algebra is just A tensor B as K vector spaces. And then the multiplication is given by permuting the central, the two elements in the center, B and A prime, and then just adding the corresponding unit element from the base field coming from the bicharacter. An important thing to notice is that the Hochschild cohomology here is bigraded. We have a grading coming from the direct sum that we took of the X groups, and then we have another grading coming from A and B already being graded algebras by these commutative groups. So a few years ago, in 2017, Grimley, Nguyen, and Witherspoon proved that under some finiteness conditions, we can translate Li and Zhou's result fairly close. So we can take this bi-graded Hochschild cohomology where we fix in the second degree some f prime direct sum g prime, and we take the Hochschild cohomology of A twisted by bicharacter B, and this is isomorphic to the Hochschild cohomology of A and the Hochschild cohomology of B, where the second element of the grading is f prime and g prime, and this is an isomorphism as Gerstenhaber algebras. So before we continue, f prime and g prime are just some intersections of the kernels of the bicharacter. This is just some subgroups of f and g. So this doesn't completely characterize the Hochschild cohomology of twisting by bicharacter because we are only taking some degrees, but it is true, and this is the result that we want to focus on. Their original proof of Grimley, Nguyen, and Witherspoon was cumbersome, and again they used extended versions of the Alexander Whitney and Eilenberg-Zilber maps in a similar fashion that Li and Zhou did, but this is again very cumbersome. What we did, the way we reproved it, is we used Volkov's homotopy lifting techniques, and we will get to that in a minute. But using these lifting techniques streamlines the proof and makes it much more straightforward. So the result that we have used was this theorem by Volkov, and what Volkov proved is that he defined a bracket at the chain level, so at the level of the resolutions, and the way he defined the bracket was this rather simple formula. So he just took the bracket of alpha and beta, and he put alpha and then something called homotopy lift, and then he added a degree, and then composed beta with another homotopy lift. And what he proved is that this bracket induces the Gerstenhaber bracket on the Hochschild cohomology. So what are these homotopy lifts? So this psi of alpha and psi of beta are the homotopy liftings of alpha and beta, and they are essentially nice chain maps between shifted resolutions of the original algebras. So the definition of homotopy liftings involves a specific resolution, involves a specific diagonal map, and involves a specific cocycle. And as we said, these homotopy lifts are chain maps between shifted resolutions, and they have to satisfy very technical conditions. But it turns out that their dependence on a resolution and a diagonal map is not such. So homotopy liftings, in fact, do not depend on any specific resolution and diagonal maps. And moreover, Volkov proved that for any resolution and for any diagonal and for any cocycle, these homotopy liftings always exist. So given the technical conditions that I have not given you, but those technical conditions are very restrictive, the fact that these homotopy liftings exist is rather surprising. But moreover, Volkov did not stop there. He also proved that this induces the Gerstenhaber bracket in cohomology, which is absolutely fantastic and extremely powerful. It is notoriously difficult to compute the Gerstenhaber bracket, but having such a specific formula and explicit too is quite amazing. So I must say that this result was inspired by work of Nguyen and Witherspoon, who earlier in 2016 they did similar work concerning now what are specific cases of these homotopy liftings where they focus on COSUL-like resolutions. So these homotopy liftings are the extremely powerful tools that we want to use to prove to reprove the theorem of Grimley, Nguyen, and Witherspoon. And the way we do this is by computing explicit homotopy liftings. So that's what we did. Given two resolutions, P and Q, and given two diagonal maps for those resolutions, delta Q and delta P, we found that this formula gives an explicit homotopy lifting of the cocycle that we find by twisting alpha and beta, where alpha and beta are cocycles of the original resolutions. So the important part in this formula is how explicit it is. Like given homotopy liftings of alpha and beta, we are able to give an explicit homotopy lifting of the twisted tensor product. And this allows explicit computations which again is something extremely rare in the world of Gerstenhaber algebras, which are extremely difficult to compute. The way that we proved this was the way that we proved was just following the technical conditions by Volkov. You just check that every single condition that he requires for something to be a homotopy lifting is satisfied, and you need to play with causal signs. I need to play with certain isomorphisms of resolutions, but at the end of the day, it does work. Once we have this, we can pick up some low-hanging fruit, and we can look at what are the possible options continue with this. So once we have this explicit homotopy lifting, it turns out that by slightly modifying it, so you may see here that we have a twist in a few spots. So by slightly modifying it, we are able to use the exact same formal proof. We are not proving Li and Zhou's result as a corollary of Grimley, Nguyen, and Witherspoon's result, although it is. What we are doing is we are reproving it using exactly the same formalism that we used to prove the original theorem, without almost any changes to the homotopy lifting. So this suggests that although finding homotopy liftings may seem like a daunting task, in practice, this may actually be feasible. And we can ask, like, what are other results that could be proven in this way? And in fact, we expect that many others allow a similar proof by these homotopy lifting techniques, including some results that are not yet known to be true. Further applications of Grimley and Witherspoon's result is the computation of the Gerstenhaber bracket in some quantum complete intersections of this type, taking an algebra on two variables and quotienting it out by degree 2 elements. And these computations are also expected to be solved explicitly using the homotopy liftings that we found. So it turns out that the first Hochschild cohomology of these quantum complete intersections is usually a finite dimensional abelian Lie algebra over which the full Hochschild cohomology is a module where the generators are the common eigenvectors, with one of the exceptions being where Q is 1 and the characteristic of the field is different from 2. And in that case, the first Hochschild cohomology of these quantum complete intersections is actually isomorphic to the Lie algebra GL2K. And it still acts on the full Hochschild cohomology, but now it's a more complicated action. Another application of these techniques is computations of the Gerstenhaber algebra structure of the Jordan plane. So this was first computed by Lopes and Solotar, and they used technical machinery involving spectral sequences. But the methods that Kardag, McFate, myself, Ocal, and Witherspoon used last year were much more elementary, with the exception of Volkov's homotopy lifting techniques. And the way that we computed this Gerstenhaber algebra structure is by seeing the Jordan plane as a twisted tensor product with the twisting map given by permuting the generators in degree 1 and adding x squared to the result. So from Volkov's theorem, it now may seem that the way to proceed is just find homotopy lifting techniques, apply Volkov's result, and you immediately get the Gerstenhaber algebra structure that you desired. So the use of Volkov's techniques seem to be the way of tackling this type of computational problems from now on, and they should enable rather elementary computations of examples, which is what we need. We need more computations. We need more examples, rather, of Gerstenhaber algebra structures. And this being said, I would like to thank you very much for your time.